So yeah, we have used the Cape Open here to investigate the carbon capture and transportation value chain, and in particular what impact impurities might have on the cost for this. Maybe a little about my background. I'm from the Technical University of Denmark, a chemical engineer, worked 8 years in FLSmidth with cement plants in the R&D department. And then in 2008, I started in Alfa Laval to work on marine scrubbers. And yeah, that has been very exciting. In 2017, I started my own company here, consulting company, ECA Engineering, where I have advised many ship owners on the installation of marine scrubbers. But that market is going down the hill. Now the ships are looking into completely different types of fuel, ammonia and so on. So now I have started to look more into carbon capture. I think that's very interesting. A short outline here of my presentation today. First, I will talk a little bit about the carbon capture and storage value chain and how I believe process simulations can contribute to lowering the cost of this. Then some considerations I've had about the choice of software. Also some thoughts I've had about the business model. This is a small enterprise I have, so I need the money to spend time on it. And then I will at the end give some example and status of the work. This study is not completed yet, so it's more a status than final conclusions I can provide today. I had these customers from the marine scrubber installations, many Danish ship owners, and I were contacted by Navigator Gas actually here in Denmark, and they asked me if I could help to look into the optimal ship design for CO2 transportation, liquid CO2 transportation, and they were in particular concerned about what impact impurities might have on that. And of course, they could just put a box around the ship, and they would end on in saying that the cheapest, from their point of view, would be to transport the CO2 just around the triple point, about 7 bar pressure and minus 55 degrees C. But what if we look at the whole value chain for the CO2? Would that also be optimal? Because that low temperature and pressure will require a very high purity. I'll come back to that. And that might imply some cost on all these processes. So yeah, I've started to actually just guess some cost here for that's the red numbers. That's purely guess in the beginning here. What it could cost in case of different purities. So yeah, we don't know in the beginning actually. So that's actually the goal of this study, is to learn a little bit more about it. And I'm sure process simulations can help in answering this. And then if we get some simulations up running, the idea is also that we can actually discuss with different emitters the type of flue gas and how we could contribute to the whole value chain. So process simulations, I think yeah, it's an obvious tool for me with my background, because the emitters they are not having these processes up running yet, and they need to overcome this heat and unique situation. They don't know what are their compositions, so we need to help them with this. Also, this CO2 transportation is strongly coupled both to the upstream and downstream processes, and so we cannot just consider the transportation alone. And then I consider that actually many of these unit operations are not that complex. It's really basic from a chemical engineering point of view. So we can actually simulate many of these things. And of course, the value chain, it's too big. It's going to be very, very expensive to capture the CO2, and it will be too slow to just build it and try all the different options. So in more details, we can say, okay, we can simulate process flue gas. I have a past experience with the cement plant, so I have actually made a model for a cement plant simulation, so we can get the exact flue gas composition and heat balance for that. But that's easy to actually change to power plant or waste incineration plant. It's just a matter of the fuel. And then, we have a CO2 capture. The amine scrubbing is the most mature solution, but I'm sure that there will also come many other options in the future. But so far, I've only had time to look into the amine scrubbing. And then we get a concentrated CO2 stream out of the amine scrubber, which we need to compress and cool to get a liquid CO2, which we must store in a tank and load on board the ship when that arrives to a port. And then there can be different options. The ship could sail to a hub or go directly for injection out in the North Sea or wherever it's going to sequester the CO2. But also there we need basically the same equipment, a compressor, heat exchangers for the sequestration. So some considerations regarding the choice of simulation software here. Of course, the ideal would be to model everything from the bottom here, to have all the unit operation, all the parameters, all the thermodynamic in place. So that's really what I would like to do, but I don't have time for that. And this is what customers usually are asking about, the return of investment for a ship or all the equipment. So we need to get to the return of investment, we need to estimate the capex and the opex, and the opex, that's the energy consumed basically, both for sailing the ship and for running all the compressors, the amine scrubber and everything. And I think when communicating here with my customers and also in my previous positions, I found out that it has to be in the unit to communicate with managers and other is US dollar, in this case US dollar per ton of CO2. Then you have the communication line. If I start talking kilowatt hours or kilojoule per mole or something, it's, you lost 90% of your audience. So, but it's easy to convert for us. So I usually try to end up with that. So the choice of simulation software, I have experience with Excel, of course, Pascal, we learned at the university 30 years ago, Fortran also, MATLAB was also introduced at that time, C++, Aspen, we touched upon at the university, CFD I worked with. In FLSmidth, we used some ASC chemistry. It still exists, I can see. In Alfa Laval, we used partly EES, but also MATLAB. And in FLSmidth, we also used GPROMs for making dynamic simulations. So I have, tried all of these types of software, more or less. But for some reason, I've ended up with building up many functions and sub-functions during the last 25 years in MATLAB, and so that became my choice here. But unfortunately, there is no inbuilt thermodynamic or chemical unit operations in MATLAB. So that was why I contacted MATLAB or Cape Open here, and fortunately, Amsterchem, Jasper helped me to connect with this MATLAB K-Open thermal socket. And yeah, I want to make a direct link to sale and to customer with my graphic user interface and process diagram and also bill of material. It's also a matter of cooperation internally and externally. If we have a good graphic user interface, actually someone who are not chemical engineers as background can also use the software to a certain extent. So yeah, it's not only focused on the chemical process engineering. Yeah, this is I think many of you can recognize this is a life of a typical process simulations engineer. You are dragged into all these IT details, connections, interfaces. You have your boss pulling in you and say, when do we have the return of investment calculations? And then you have your wife. You have to do other things also than working with your computer. So this is really the dilemma I've been in for all my life, I think. Some few thoughts about the business model. I'm sure there's a huge potential in process simulations. If we, for example, look at the International Energy Agency, how much CO2 they forecast needs to be captured, and we look at these $100 per ton, it is billions of dollars every year if this is not optimized, that are simply lost. So this is certainly an area we can help. In Denmark, there is a lot of focus. We have something called demonstration projects, which are public funded. But the word, is demonstration. They want to see something erected out here at our cement plant, for example. There's not so much, unfortunately, attention on what simulations can do. But when I look at what they're doing and how many millions they spend on these demonstration projects, I just consider how far we could get with simulations. We can simulate many of these things. Yeah, I think I have mentioned this. It's also, I think sometimes when I talk with customers, a bit disturbed by buzzwords like Internet of Things, artificial intelligence, especially big data. Why can't we just use artificial intelligence and it will give us the optimal solution? And then, yeah, I think also these process simulations are rarely acknowledged when millions really are saved in the process simulations. Then this parrying work is often forgotten. So we need, I think, a healthy business model to ensure that we have resources for success in this. So I think we need to also explain about the possibilities in public, what we can do. We need, of course, to pay all the developers for their huge effort, especially when we have success. And not at least we need to cooperate. So this conference is good, but we also need to attend more commercial conferences, I think, and to bring out our message here. And then, yeah, I will show just some examples. I used MATLAB, and I start always just to get the heat and mass balance up running in a very, simple way. And then if I have time, then I can start to dig into further details. This is a cement plant where I know what is the approximate heat balance in practice, 760 kilocalories per kilogram of clinker. Everybody know that. So my simulation should turn out with that number, so that we can choose different fuels for the calciner and the rotary kiln. And so this is actually fine to get the flue gas stream composition as required to continue the simulation in this case. Yeah, I built a sheet here to ensure that the balances are okay, mass and heat, and all the streams we can see here. Then I have made this CO2 scrubbing model, the amine scrubber, with an absorption tower and a desorption tower, and a big heat exchanger in between for the amine running around here. Again, we have the complete heat and mass balances to fit here. And then I have also tried to add some cost for electricity, so we can estimate what are actually the OPEX for this. Then on the liquefaction model, and this is where I have integrated with the Cape Open thermal socket. First, a flow sheet, and as it's easy just to increase the number of compression stages here. It will automatically generate a new flow sheet. And let's see. Then I think that's a good thing in MATLAB. That's the possibilities to really visualize what you're doing. So here I have the compression cycles, the temperature, the entropy as a function of the and the pressure of the y-axis. You can see how we compress and how we flash it and get the liquid. And again, a sheet for the heat and mass balances for this process. Details of all the streams. There's a purge stream because the impurities need to get out of the system. And then I've just made a possibility here to optimize the purge in terms of power consumption. So in this case, it's around 50%. Some settings. And then finally, I can compare different simulations here and see the impact. And we can clearly see that now this is a case with 98% CO2. If we 231 kilowatt hour per ton of CO2, if we increase to 99% CO2, we go down to 159 or 160 kilowatt hour per ton CO2. So it's definitely an important parameter, the purity here. Here I have the setting, choice of thermodynamic model. I have used the TEA, Cape Open, and how my solutions are converging here. And then, I've also looked on the liquid CO2 transportation. You all know this phase diagram is for pure CO2. But what will happen if we add impurities? And then we will start to form a two-phase region here. And then I foresee some issues if we try to add nitrogen here. Imagine you have a terminal here, for example, with it could be 8.5 bar pressure in the terminal, minus 54. It has to be loaded on a ship here, but if that ship only has 6.5 bar pressure, some of this nitrogen will flash off with CO2, and then the tank on board the ship is it's not completely insulated, so heat will penetrate during the transportation. So you can easily end here, depending on the amount of impurities, that you have less CO2 when you get out to the field for sequestration, if there are too many impurities and if the system is not designed correctly. So it's it's things like that I'm using Cape Open for. This is another quick app I have made as a web app, so it's easy to access for everybody, because there are different standards for the purity, and it's not so easy for non-chemical engineers just to convert from dry basic to wet basis, for example, and see if a certain analysis comply with these purity standards. So it's an easy way to, and you can choose different standards. Yeah. So I think that's what I can present of status for today.
Thank you, Jens Peter. So